Welcome to the Deep Dive, the place where we strip away the noise and get straight to the knowledge nuggets you need. Today we're diving into a topic that, well, it sparks genuine debate in pretty much every software engineering department I've ever seen: code coverage.
Oh, absolutely. It's the metric that for decades has been sort of held up as the definitive sign of a healthy code base.
Like gold standard.
Exactly. You see 95% coverage, you feel safe, you see it 100%, and, you assume perfection.
And the general wisdom, intuitive, right? The closer you get to 100%, the more resilient your software must be. But our sources today, a collection of engineering write-ups, analysis papers, and a really great internal case study, they all suggest something profoundly counterintuitive.
That's right. Our core premise is this. While perfect, 100% coverage is often theoretically achievable, chasing those last few percentage points is often not just expensive, but actively detrimental.
Detrimental, as in it actually hurts your code.
It can, yeah. It can harm your long-term code quality and its maintainability.
That is a huge shift in thinking. So we're going to look very closely at a specific software package. It's called MyWheel, which boasts an impressive 98% coverage score.
And we're going to argue that the missing 2% isn't a failure at all. In fact, it's a perfect illustration of maturity, pragmatism, and just smarter software engineering decisions.
Okay, so our mission is to unpack the specific challenges hidden in that final 2%.
And give you a clear, actionable playbook for testing smarter, not just testing more.
All right, let's start with the facts of the case file. The MyWheel package is highly stable, it's widely used, and our sources confirm its total test coverage sits right at a powerful 98%.
And this is a test suite performing at an elite level. I mean, to give you a sense of their diligence, several core utility modules, things like components handling arrays and doubly linked lists, they achieved a flawless 100%.
Every single line executed.
Every line, every possible branch taken. But as always, there's an outlier, and that's where our lesson really lives.
And that would be the module bpq.py.
Exactly. It manages a core internal data structure, and it sits just shy of perfection at 95% coverage. There are 3 total lines that are not being executed by the test suite.
3 lines. That's all that stands between this entire professional code base and what so many developers consider the holy grail.
So the essential question for us is, what are those 3 lines, and, are they just bugs waiting to happen?
And what the investigation reveals is crucial. The gaps are not indications of overlooked functionality or some major flaw. They actually fall into 2 very distinct categories, and both point to deliberate trade-offs made by experienced developers. We need to dissect those.
Let's start with the first category then. This is the one that often accounts for the most frustrating missed coverage points: defensive assertions.
Right, so 2 of the 3 uncovered lines in bpq.py are these simple internal checks, assertions deep inside the structure that verify internal constraints, like making sure a specific index value is always positive.
And what's really key here is understanding the intent of that code. These asserts are not designed to handle, say, user error or standard API usage.
No, they're internal guardrails.
They're purely defensive checks, there to catch programming errors. So if a developer internally misuses the queue's data structure during a modification, the assert trips and the whole thing blows up immediately.
There are safeguards against internal logic faults, so if the code is executing correctly, those lines are never ever supposed to be hit.
Precisely. And if they are hit, the program just halts with an assertion error.
Okay, but of course, the developers want to confirm that these assertions actually work. So they write tests designed to violate the conditions on purpose.
Exactly. They use tools like Python's pytest.raises assertion error to check that when you feed it bad data, it throws the expected error.
So the test passes, the error is verified, yet the coverage tool still shows those lines as uncovered. Why is that specific frustrating thing happening?
This is where we run smack into the limitations of the coverage measurement tool itself. When an assertion fails, the execution sequence is very specific. The code hits the assertion, determines the condition is false, and immediately starts to raise the exception.
And before the coverage tool can even register that line as executed, the whole process is short-circuited by the exception.
You've got it. The exception handler, which is the test framework, PyTest in this case, jumps in, catches the exception, and the code execution path just terminates right there.
So the test suite confirmed the behavior, that the code correctly fails when it should. But the metric, the tool tracking the line execution, it never fully registered the assertion line itself because the code blew up too fast.
It's an artifact of measurement logic, not a flaw in the test coverage. The test quality is high, but the score is low.
So what did the MyWheel team do?
They made the pragmatic choice. They used their coverage configuration file, the .coverager task, to specifically exclude lines containing these defensive assertions. They effectively told the tool, look, we know these are covered by functional failure tests. Don't penalize our score for it.
That makes perfect sense. It's managing the tool to reflect reality rather than, managing reality to fit the tool.
And it keeps the focus on real, untested logic.
But that only accounts for the intentional omissions. We still have that final remaining gap, the truly elusive code that wasn't excluded by configuration.
Yes. These fall into the second category. Complex and often, frankly, unreachable conditional branches. This is where the work gets disproportionately hard.
We're talking about corner cases deep within state-heavy methods, right?
Yeah.
Things like increase key or modify key inside the priority queue.
Exactly. Specific paths that only open up under incredibly rare and complex conditions. For example, there's an early exit condition and another path within the iterator logic, the piece of code that defines how the queue moves from one element to the next.
Okay, let's step back and think about the difficulty here. Why does hitting one small if statement buried deep in a utility method become, a nightmare?
It comes down to control and setup complexity. To hit that one condition, you might have to execute 20 previous function calls in a very precise sequence. You have to manipulate the internal state of this complex data structure, the queue, until every pointer, every length counter, and every value is positioned just to allow that specific tiny branch to execute.
It sounds less like writing a test and more like building a Rube Goldberg machine.
That's a perfect analogy.
You're creating this impossibly complex setup just to flip a single tiny internal switch.
And you're not testing the public contract. If I add 2 items and remove 1, I get the right result. You are testing the internal mechanism that handles an extremely rare combination of internal state flags.
And for external tests, manipulating those internal knobs, especially in complex iterator logic, that sounds notoriously unreliable.
It is. The test setup becomes inherently brittle because it's so tightly coupled to the structure's current implementation.
And it must require a vast amount of setup code. You might spend 10, 20 lines of code just trying to position the data structure to hit one line.
And then you have to hope that setup doesn't break every single time the code is slightly refactored.
So if a line is this hard to reach, requiring 10 times the setup complexity of a normal test, that's where we hit the crucial pivot. The high cost of perfection. What are the negative consequences if the team decided, we're going to spend a week eliminating that final elusive conditional branch?
The consequence is an exponential diminishing return that actively creates maintenance debt. The closer you get to 100%, the less ROI you get, and the more collateral damage you inflict on the test suite itself.
Okay, so let's break down that damage. What's the first thing that breaks when teams force perfection?
Overly specific tests. To hit that rare condition we just discussed, you have to write a test that is completely implementation aware.
It's testing how the code works, not what it does.
Exactly. It tests how the queue stores its data internally, rather than what happens when a user calls queue.pop. And this is fundamentally poor testing practice. Good tests verify the observable contract. Bad tests verify the plumbing.
And when you verify the plumbing, that immediately introduces the second, and I would argue, most harmful side effect.
That is brittle tests. If your test suite is implementation aware, it just constantly breaks. A developer decides to rename an internal variable or maybe switch from a dictionary to a tuple to increase performance, a non-breaking change to the external user.
But if the test was checking that internal plumbing, it fails.
It fails, and now you force developers to spend half their time fixing tests that identified 0 actual bugs.
The moment a test fails without uncovering a real bug, you've increased maintenance overhead and, more importantly, you've destroyed developer trust in the suite.
Absolutely. The developer starts viewing the test suite as a liability, not a safety net. And that leads directly to the third point, unmanageable complexity.
You mean the tests themselves become monsters?
Yes. Chasing those final corner cases leads to convoluted, Baroque test setups that become harder to read and maintain than the original production code. Imagine a 100-line test setup just to hit a 5-line conditional. Developers hate that.
When you weigh all that brittle, complex, implementation-aware code against the purely aesthetic pleasure of seeing a green 100% score, the verdict becomes crystal clear.
The remaining 2% in the MyWheel package is a mark of intelligent development. They stopped when the effort required outweighed the gain in quality and started damaging the integrity of their test suite.
Forcing 100% would have traded genuine maintainability for a vanity metric.
That's the bottom line.
So we've learned why you shouldn't blindly chase the metric. Now let's synthesize these findings into a practical playbook. How do we test smarter, using coverage as a guide, not a dictator?
We have 3 essential rules that come out of this deep dive.
Okay, playbook rule number 1. Adopt risk-based coverage. This means shifting your focus from, is the line covered, to, does the coverage actually reflect the risk?
You have to prioritize complete coverage for your public APIs, high-risk financial logic, anything that interacts directly with external systems. The code paths users are definitely going to encounter.
But you don't waste time on internal error handling or utility code that is only called by one other perfectly tested function.
Exactly. The question you need to ask isn't about the line count. It's, if this specific function fails, what is the consequence? Use the answer to that, a data loss event, a critical user interruption, to determine your testing effort.
That reframes testing as risk mitigation, which is inherently a more mature approach than just line counting. Okay, playbook rule number 2 is about changing the way you write tests to achieve better coverage with less complexity.
Right. We need to talk about property-based testing, a technique used successfully in the MyWheel suite. This is a fundamental shift from the example-based testing most of us were taught.
Where you test input 5 yields output 10.
And if you have 1,000 possible inputs, you only end up checking a handful. Property-based testing, or PBT, using tools like Hypothesis, it tests the invariance and properties of your code. An invariant is a condition that must always be true no matter the input. You tell the framework, the list size should never decrease after an element is added. Or, if I sort this list, the result should always contain the same elements as the input.
Wow, that's a huge shift. Instead of checking a few specific scenarios, you're testing the fundamental rules of the function.
And the benefit is immense. The PBT framework then automatically generates hundreds, even thousands of highly diverse, often malicious inputs for you, empty lists, huge lists, strange number combinations, odd data types.
And in doing so, it hits complex edge cases and conditional branches that a human would never have even thought of.
And you get superior coverage, both line and branch, with a tiny fraction of the manual test writing effort. It's far more likely to find real subtle bugs.
It sounds like the antidote to writing those horribly complex Rube Goldberg setups we were talking about earlier.
It is. It shifts the burden of finding the corner cases from the human developer to the machine.
And finally, playbook rule number 3 brings us back to that crucial lesson on maintenance debt. Balance coverage with long-term maintainability.
Right. Remember, your test suite is a living document and a long-term asset. You have to prioritize readability. If a test takes 5 minutes to read and understand, it's a bad test. If a complex test is written to protect one tiny line of code, but breaks every time the code is refactored, you've created a liability that outweighs the value of the protection.
So the ultimate test of quality then is decoupling. Test the contract, what the function promises to do, and completely ignore the implementation, how it gets it done. If you can make substantial internal changes without breaking your tests, you have built a maintainable safety net.
A test suite that is easy to read, easy to update, and focused on risk is far, far more valuable than a fragile 100% score that just demoralizes your developers.
That brings us to the conclusion of this deep dive into what we're calling pragmatic coverage. The central idea is pretty clear. Code coverage is a vital diagnostic tool, but it is not a trophy to be won.
The goal is the creation of a robust, maintainable system, not the achievement of some arbitrary percentage. We've established that the last few percentage points of coverage often demand a cost in complexity and implementation coupling that just far outweighs any benefit, leading directly to brittle, expensive test suites.
So next time you look at a coverage report, don't just ask what the percentage is, ask why those final lines are missing.
And here's a final provocative thought to consider as you rethink your testing strategy. We know that tight coupling leads to test fragility and maintenance headaches. So, if developers are so focused on tracking the simple numerical coverage score, how can teams begin to establish metrics to measure and track the fragility or brittleness of their test suite itself? We need a metric for test quality, not just test quantity.